Okay, good morning all of you. My screen is visible. Anybody?
Yes, sir.
Okay, thank you. So we'll see today three-phase semi-converter with the different loads. So it may be R load or RL load. Anyhow, it is inbuilt with prevailing diode, or we want to use prevailing diode separately, we can use it. But both is same. In the lower group devices are the diodes. That's why we no need to use the separate prevailing diode also. But if required, you can use it. The both cases response or output is same. In this, what we discussed in the previous class, there is a 3 pulse midpoint converter as well as the 3 pulse 3 pulse midpoint and 6 pulse midpoint we discussed in the previous class. So now the same thing, bridge rectifiers. So here we can see there is a 3 pulse bridge rectifier. So this one is a 3 pulse bridge type, and 3 pulse midpoint type. We noticed the response there, the output is phase voltage. So if you see the diagram also in the previous case, this one, each phase we connect one thyristor, and like that A phase, B phase and then C phase, and this will be connected like this. In midpoint will connect as a load. Let it be, this is our 3 phase half wave rectifier or a 3 pulse midpoint converter. Any of the device is conducting, whether A phase or a B phase or C phase, if anything is conducting, then you can see that the voltage across the load is same as the A phase voltage. Suppose this one is conducting, output is coming like this, then the phase voltage is the output voltage. Or if B phase is connecting, the phase voltage is B phase voltage, and T3 is conducting, then the output is same as the C phase voltage, like this. So from the previous analysis, that is a midpoint case, each phase voltage is your output, means the particular phase the device is conducting, then the output is same as that particular phase voltage. But whereas in this case, what we are going to discuss is here 3 phase semi converter, or you can say that is a 3 pulse bridge rectifier. So in a 3 pulse bridge rectifier, your output is same as the line to line voltage. That is the difference between midpoint case and bridge case. So in a midpoint converter, output is a phase voltage. In a bridge type converter, output is a line to line voltage, because you can see here upper group devices and lower group devices are there. Let's consider upper group devices are 135 and 462 is a lower group device. We can use the numbering any other way also, 1 2 3 or diode D1 D2 D3, like that also we can give it. But this sequence what I am providing here is a 135 is upper group device and 462 is a lower group device. So this case, one reason is there to provide like this, whereas otherwise also we can use it normally. Just a minute. So what we can use is here, let 135462, if we use like this, our sequence or conduction order will be the simple order. So we can see there is a conduction, let it be 1 2, then 2 3, then 3 4, 4 5, 5 6, 6 1 and so on, cycle is repeated. No? So this is the order we can get it. If I use the numbering 1 3 5 and 4 6 2, if you place the easy way to remember after 1 2 which device is going to conduct. So 1 2, then 2 3, then 3 4, 4 5, 5 6, even for the 6 pulse converters also. That is only the reason we placed the names will be like this, but no such rule we have to use only these numbering anyway. But the different is if we change here, order also going to be changed. That remembering is a complication. That's why we can use this the reason. Now why output is line to line voltage, whereas in the midpoint case it is a phase voltage. So now we can see suppose any two devices are conducting, then at what instant which device is going to conduct we will discuss after this. At moment let consider T1 is conducting and also something D2 is conducting some particular instant. If T1 and D2 is conducting, then what is the your output voltage? Now we can see here if T1 is conducting, then current will pass like this, A phase, it goes to the T1, then it goes to the R load, then D2 to out. Then what is our output voltage where load is connected? One end is connected to A phase, other end is connected to C phase. Then what is our output voltage? VAC. Your output voltage is VAC if T1 and T2, T1 and D2 is conducting. Similarly, in some other instant, let it be T1 and D6 is conducting. Then what is your output voltage? Then again it goes to the A phase T1, then R phase, then D6 to out. Then your output voltage is equal to VAB. VAB. Always start with positive and then means here is a positive group device, this is a negative group device, or upper group device and lower group device. Suppose T5 D6 is conducting, then what is our output voltage? It starts with positive, we can get C, then it goes to the T5, then R load, then D6 to out. Then what is your output voltage? VCB. Your output voltage is VCB. So like this, we can easily identify what is our output voltage any particular instant if two devices are conducting. Similarly, if suppose the freewheeling diode is conducting, then what will happen? If this diode is conducting, means it is a parallel to the load, then automatically it is a short circuit to the load terminal. Then your output voltage will be 0. If freewheeling diode is conducting, if FD is conducting, your output voltage is 0. Like this, we can identify and we can shade your output line to line voltages in the load side. But now, when this diodes is going to conduct T3, T1, T3, T5. Similarly, when this diodes is going to fire. So it is very simple logic. Suppose A phase you can see. A phase is connected to this point. So let it be, this is the A phase connection. A phase is how many devices we have? T1 is there. Another one is a D4 is connected to A phase only. Now A phase anode is connected to T1 and cathode is connected to D4. So from this, when this device is going to forward bias, now we can see one instant, whenever A phase is positive, then what will happen? It is connected to anode, no? So T1 is going to be forward bias. Then if A phase is negative, then D4 is going to forward bias. So like that, other phases also. Suppose B phase. So if B phase is more positive, then automatically T3 will forward bias. If it is a more negative, D6 will forward bias. Similarly, C phase. So if it is more positive, D5, more negative, D2. So at any particular instant, you can see the all the phase voltages, A phase, B phase, C phase, and from that, which is more positive among all the three phases, corresponding device is going to forward bias. Suppose at omega t is equal to 45 degrees, not alpha, I am telling omega t is equal to some 45 degrees. At that line, you can see at omega t is equal to 45 degrees, you can observe what is the A phase magnitude and B phase voltage and C phase voltage at omega t is equal to 45 degrees or 30 degrees or 60 degrees or any instant. It's not a particular, any value of omega t. You can find what is the A phase voltage, B phase voltage and C phase voltage. If A phase voltage is more positive than B and C, what will happen? A phase device is going to forward bias, positive device. So if it is more positive, then T1 will forward bias. Suppose same instant, some other phase may be negative and that C phase, let assume that more negative. If C phase is more negative, then what will happen? D2 will be forward bias. So at that particular instant, we can easily identify what are the devices are going to forward bias. One thing we notice, suppose if it is A phase is more positive and C phase is more negative, then you can see that T1 and D2 going to forward bias. And let assume that firing pulses also available for T1. For D2 not required, it is forward bias means automatically it will start conduct. And now T1, if T1 is positive and D2 is negative, then what is your output? This is conducting and this one is conducting. Your output is V, A and C. Your output is VAC. Like that, we can easily identify the particular instant which devices are going to be forward biased, and we need to check during that instant what we have is, firing pulse is available or not, we have to check. If that firing pulse is not available, then even though the device is forward biased, for the upper group devices will not trigger if firing pulse is not available. But lower group devices are going to change. So like this, we have to identify at any particular instant what are the devices are going to forward bias and what is the output voltage. Two things we need to identify. First thing is which devices or which phase is having more positive and which phase is having more negative. That is the first thing. And second thing, once if you identify that particular devices, then check for the firing pulses for upper group devices alone. Then you can shade that output line to line voltage. These are the three steps we have to find. In this, one more thing you must remember here, even if you use RL load, it is not only R load, you can use the RL load or RLE load, anything you can use it. Your output voltage will never give as a negative because of the freewheeling diode is available. If the freewheeling diode is not available also, lower group devices are the diodes. Any one of the leg will act as a freewheeling diode at that particular instant. That's why we can see that here in the case of semi-converter, will give only the first quadrant converter. That's why I mentioned here 0 to 180 degrees. Whatever alpha you want to put for any load, R load or RL load or anything, you will get only positive output voltage. You don't get any negative output voltage because of the freewheeling diode is available. So that is the reason you can see that it will be the first quadrant converter or motoring operation only. This will operate only in the first quadrant operation. So there is a rectification mode of operation only. It never give as a inversion mode of operation. Whereas in the fully controlled rectifier, it will give first quadrant as well as the fourth quadrant operation. But here will give only the first quadrant operation irrespective of the load. The load may be R load or RL load or RLE load. You will give only first quadrant operation. The reason behind this is a freewheeling diode must. It must in the sense it is there already. Even if separate freewheeling diode is not used also, one of the leg will act as a freewheeling diode. It will be as a what you call it as a act as a freewheeling diode. It will make it as a short circuit during after pi instant. So this is the brief introduction. Now we'll see how waveform we need to draw. Here the thing is we need to draw waveform supply voltage, then firing pulses, then line to line voltage you have to draw, and that line to line voltage you have to shade it. So that is the case of semi converters as well as the full converter output voltage representation. First thing is you have to draw the phase voltages, all the three phase voltage. Second one is pulses. Third one is line to line voltage you have to draw. So this is the sequence. Once if you draw the line to line voltage and see the phase voltages and see the firing pulses, and then what is your output voltage you can identify, and you can shade your output voltage, whether it is a AB and then AC or BC or BA, then CA and then CB. Like this, we will get all the line to line voltages. Once if you know line to line voltages, we can easily shade the particular instant. Now we can see here, this is our supply voltage, and here also you need to identify the crossovers. So that is very important thing for all the three phase supplies. From which instant onwards device is going to be forward bias. So how many devices we have here? 3 thyristors, 3 diodes. We need to identify the crossovers for thyristors. For diodes, automatically which is the more negative instant, that diode is going to be forward bias. But we no need to check the firing pulses. So then we can see that one thing is Vs, that is a T1, T3, T5. At that instant, what will happen? Here we can see that supply voltage is given. T3, T5, T6 is the positive crossovers. So now, why that instance I mentioned as a positive crossovers, you can see here. One thing for A phase. So what will happen? A phase is started at this point onwards. This is the omega t, x-axis is omega t. Omega t is equal to 0. Let it be, this is the starting point. If omega t is 0, then what will happen? A phase is not a forward bias. Reason is, you can see at this line, the omega t is equal to 0 line, which phase I want to know what is the VA, VB and VC. No, what will happen? VA, A phase magnitude is 0, then B phase magnitude is negative. You can see this is a negative, and C phase magnitude is a positive. So C phase magnitude is a positive. That means for A phase I am representing omega t is equal to 0 instant. A phase is not a forward bias. This one is not a forward bias, which will find B phase is a C phase is the forward bias because it is a more positive than other phases. That's why we can see here what we can represent is A phase will not forward bias at omega t is equal to 0. And now you can see at omega t is each line is 30 degrees I mentioned. No? Suppose at 15 degrees. At omega t is equal to 15 degrees and you can check it. So 15 degrees, this is the C phase, this one is A phase, this one is a B phase. Then what is the VA? VA is a positive only, and then VB is a negative and VC is a positive. But among these two, which is more positive, that will be forward bias. And here you can see that what you can have, A phase is less positive and then C phase is a more positive. So that's why this C phase device will be forward bias. And then B phase device is also for the diodes it will conduct. But one thing I mentioned, no, two devices has to conduct at any particular instant. What is the two devices? One is a positive group device, another one is a negative group device. One must be upper side, one must be lower side. 135 is upper side, 462 is a lower side. So at any instant, one must be upper, one must be lower. So now we can see in this omega t is equal to 15 degrees. What are the devices are forward bias? VA is a positive only but less positive, and VC is more positive. Then the C phase device will be forward bias. So this is A phase, B phase and C phase. C phase positive device, that means 5 device is fifth one is forward bias, and then B phase is more negative. So B phase is negative means what? Sixth device is conducting. Then your conduction will be 5, 6. So what is your output voltage? B phase is more positive and C phase is more negative. VBC is the output voltage at omega t is equal to 15 degrees. And here we have to check at 15 degrees whether C phase firing pulse is available or not. That moment just I am explaining how to identify device forward bias and what is our output voltage. If B phase is not having firing pulse, then B phase device will not conduct. Which is having the firing pulse, that device is going to fire. So that is the identification. Like that, at any particular instant, now I will write at omega t is equal to, anyone you can answer at this point, omega t is equal to 120 degrees. What are the devices are going to forward bias? Now we can see similarly VA, VB and VC you just identify, or by seeing itself is easily understand. This is A phase is more positive and B phase also positive but less positive, and then C phase is a more negative. So then what will happen? This will be A phase device is forward bias and C phase device will be forward bias, but C phase is a lower group device and A phase is a upper group device. So now we can see that VAC is your output voltage for that particular instant. Now we can see firing pulses also. So now that is clear, all of you. Just check it any particular. If somebody is asked that omega t is equal to 300 degrees, which devices are forward bias? How will you identify? At 300 you can see C phase is more positive and then A phase is more negative. Then what is your output voltage? VCA is your output voltage. If you want to know the device conduction also, this is a upper group device is fifth and lower group device is a 135, 462, no 4. So that means your output voltage will be VCA, device conduction are 4-5. So like that, just for sequence order, whether it is a 5-4 or 4-5, both are same. Only remembering purpose, we use 1, 2, then 2, 3, then 3, 4, 4, 5 like this. So this is a 4, 5. Then after that, what will happen? 5, 6 will come. You want, you can check it. So there is a fifth one, and at this instant, any particular instant, you can see there is a B phase is a sixth device, and C phase is a fifth device. So like this, we can easily identify what are the devices are going to fire at any particular instant. So now first one we are to represent supply. Supply is a simply three phase AC supply you have to draw, and after that you identify the crossovers. I will identify the crossover as I explained earlier. A phase device will be forward bias only after 30 degrees, because below 30 degrees A phase device, you can see here, less positive when comparatively C phase device. This is a C phase and this one will be as a phase. So before 30 degree, you can see that before 30 degree, C phase device is the. Hello. Now, I'm audible. Hello. Anybody? I'm audible. Hello.
Yes, sir.
Yeah. So now we can see A phase device at 30 degrees or before 30 degrees of duration. You can see that C phase is the more positive and A phase is the less positive. So that is the reason the A phase device will not conduct up to 30 degrees. Now exactly at 30 degrees, what will happen? You can see here exactly 30 degrees, both A phase device or A phase as well as the C phase magnitudes are same. So from this point onwards, A phase will be more positive. That's why this point of crossover, I mentioned X, Y, Z or something, or just crossover point. So this is the T1 crossover. Similarly, you take it as a B phase. Anywhere you can take B phase is starting here positive. From this duration up to 30 degrees, some other phase, let it be as A phase, is more positive than the B phase. That's why after 30 degrees both is same, and from there onwards you will get it as a B phase is a more positive. So like that we identify the crossovers. A phase crossover, this one, and this is the B phase crossover. This one is the C phase crossover. So like that, first you identify the crossover. Suppose if lower group devices also as a thyristor, we need to identify the lower group crossovers also for whenever it is a more negative. So for lower group devices will be forward bias whenever the particular phase voltage is more negative. Upper group device will be forward bias that phase voltage is more positive. That's all. So very common logic. For more positive case upper group device, more negative case lower group devices will be forward bias. Now we identify the crossovers. Once if you know the crossovers, what you have to do? You have to provide the firing pulses. The lower group, we can see that the which phase is connected to which device is identified, that we want to can mention. Otherwise also you can easily identify which device. Now we can see that this C phase. What is C phase device? Here from here to here is a more negative. Then C phase is connected to what? Our order is 1, 3, 5 upper side, 4, 6, 2 is a lower. Now C phase device means D2. That's why C phase more negative portion, D2 device will be forward bias. That's why I mentioned here is a D2. And similarly, this red one, A phase. So A phase is more negative. A phase is more negative means which device? 4. D4. So similarly, here is what B phase. B phase is more negative. B phase is more negative means D6. Like that, we identify the diode conductions also. Now, is it very simple? You have to draw the three phase, then identify the crossovers for T1, T3, T5, because upper group devices order is 1, 3, 5. If it is 1, 2, 3, if you mention, then this is a T1, then there is a T2 you can write here, then it is a T3 you can write. Whatever order you follow in the circuit, same thing you can represent there. So now I used, or I am suggesting you to use the 135 upper and 462 is lower, then the sequence is the same as what I am going to present in these slides. So now we can see lower group devices are identified and upper group device are also identified. Now you have to provide the firing pulse based on your firing angle. Suppose I want to provide firing pulse for thyristors at alpha is equal to 0 degrees. Now alpha is equal to 0 degrees, I have to provide the firing pulse. From where to where I have to provide the firing pulse? For alpha is 0, now we mention crossover from this point to up to omega t is equal to 0 you can put, and again here is the repeating pulse. This is again T1 because positive A phase will be more positive from this pointer. So this is repeated pulse and that is for T1. Similarly, I am writing separately for understanding, or you can club also. I will show that also. Now for T3, alpha is equal to 0, where I have to provide the firing pulse. Now you can see this is the reference, or alpha is equal to 0 for the T3. Now you can make it firing pulse, starting pulse is here because crossover point, and you can end that will be up to natural 0. You can put like this. This is for T3 pulse. This is for T1 pulse. For alpha is equal to 0 only I am telling. And now for T5, where I have to provide the pulse for T5? This is the 0 reference point. Here onwards you can measure the firing pulse up to natural 0 like this, and this side cycle is going to be repeated because here is a which phase, C phase is no more positive, anyhow pulse must be there in that portion also we can use. So this way you have to provide the firing pulse for alpha is equal to 0 degrees for T1, then T3, then T5, T5, T3, then T1. And now suppose if I want to provide the pulse for alpha is equal to 30 degrees, where I have to start the firing pulse. The difference is very simple. Once if you identify alpha is 0, then you can see pulse change. So now instead of what we can use alpha is 0, here we started now 30 degree I am asking. I want to represent alpha is equal to 30 degree firing pulse. How will you represent? Count. This is the 0. Alpha is equal to 0 starting point. From here to 30 degree you can count. So that means here. This is the starting pulse. So now you have to provide the firing pulse for alpha is equal to 30 degrees T1. So here. So this side you just discard. This side pulse is not available, you remove it, only firing pulse will start here. This is the pulse for alpha is equal to 30 degrees for T1 and similarly for T2. How will you provide? This is 0, you count 30 degrees one line, and here you have to provide the firing pulse for alpha is equal to 30 degrees. And similarly for T3, this is 0 point and you count 30 degrees, and this line will give alpha is equal to 30 degree. Like this, you are just shifting the firing pulses. So that is only the different. You can see here. Once if you shift, suppose somebody is asking draw the output voltage waveform for alpha is equal to 60 degrees. Then alpha is 60 degrees means where you have to provide the firing pulse. Simply you can see this one is alpha is 0 and this is alpha is 30. This is alpha is equal to 60 degrees. Now this line will start the firing pulse for T1 and this is 0 and then 30 then 60. So this line will give the firing pulse for alpha is equal to 60 degree. Means this side portion will not be there. You can starting itself here. This is the firing pulse and this is the firing pulse. And similarly for T3, 0, 30, 60. Here you have to provide the firing pulse for 60. Now our pulse is like this. For alpha is equal to 60 degree. So from this, alpha is equal to 30 degrees means omega t is equal to 60 degrees. That means omega t is equal to 30 degrees. Then alpha is equal to 0 degrees. That is only the difference. Omega t is equal to 30, or alpha is equal to 30 means omega t is equal to 30 plus 30. So that means 60 degrees, like this. So this is the way we have to represent. Now I will show that. So now I identify the crossovers. Then I provided the diode durations also. Then you can see for alpha is equal to 0 degrees firing pulses also. I will show you alpha is equal to something 0 degrees. So here alpha 0 means where I have to provide. This is the starting point. So this is the starting point, and then so this is the starting point. It will be like this for thyristor T1. So this is T1. From here onwards, after alpha is 0, then T3 is going to fire, and here onwards then T5 will fire. So this is the instant T1, and here is a T5, T3, and this is a T5. So like this we can provide the, again T1 will be, cycle will be repeated. So you have to provide the firing pulses this way also in the same line, from where to where T1, and then immediately T3, then T5. So like that also you can provide the firing pulse, or if you want clearly you separate what I drawn the earlier, just you draw for T1 alone. You can draw the T1 firing pulse like this. Then you draw one more line, and wherever it is started you can provide the T3, then one more line you can provide for T5 for alpha is equal to 0. And similarly you can see this what T1, then T3, then T5. So this side cycle is going to be repeated. Why this I have to provide? You can see that how many degrees next cycle is going to be provided. See that each line is 30 degrees. That means how many lines you can see? 1 up to here is T1 is there, no? 2, 3, 4, 5, 6, 7. After 7 lines, that means 7 into 30. After 210 degrees, then the cycle is going to be repeated. That's the repeated pulse. Like this you have to provide starting, then next pulse will be repeated here. That's why this duration is a 210. So after 210, next cycle is going to be repeated. Similarly for T3 we started this pulse. This is the T3 crossover, T5 crossover. We will get as a pulse like this, then the T5. So after that 210 you can count 1, 2, 3, 4, 5, 6, 7. So after 210 there is a firing pulse in this side also. Like this we have to provide based on this analogy. So whatever T1 gap is there now, in for T3 also after 210 you can see that 1, 2, 3, 4, 5 only available. So there is somewhere in this side. That's why I am not shown here. And this side also 1, 2, 3, 4 only there. If it is 7 gap, there the pulse will be there. So like this we have to provide the firing pulse for alpha is equal to 0. All of you clear? First you have to draw supply, then you have to provide the firing pulses for T1, T3, T5. So first one is a T1 firing pulse. This is the T1, if you want you can show, and then T3, then T5. So this is the firing pulse. Then third step, what you have to do? You have to draw the line to line voltage. What is the difference between phase voltage and line to line voltage? There is a 30-degree phase shift. So that's why same thing, instead of starting here, you can start somewhere here. Same thing if you draw, you can see that. So instead of starting here, for what you called as phase voltage started 0 here, but 30 degrees phase shift is there, we can start this point. So that's why this portion onwards will get shifting. Just 30 degrees is going to be shifted, and this is the line to line voltage. How will you draw line to line voltage? First, same thing, phase voltage only by shifting. Just you can know we are counting three lines 0, 30, 60, 90. This is the peak. Now what you will draw? Here you can start. This is the 0 point, and then 30, 60, 90. So again same thing. You can put like this. Again 0, 30, 60, 90 like this. So only thing is I removed this portion. That's all. So this is only same thing. What I drawn is here and here is same, but only 30 degrees gap is there. That's why you can draw a line here. Then you can draw as a line to line voltage. I will show that graph sheet also. Very simple. Instead of starting here, you start here and draw the three phase supply. That three phase supply. Now whatever you are getting here, this is a AB, BC, CA, and in between this negatives we represent positive, and here negative is there. What will happen? AB, if you represent BA, first you have to draw three phase supply only, that you mark it AB, BC, CA. Then what you want to do is whatever the negatives are there, that negatives will make it as a positive. So how will you do that? Same AB phase is there, and if you represent in the positive side, BA will get, and CA phase is there, this is a positive, and CA negative you represent in the positive side will become as a CV, like that. So whatever AC. So like this, what you want to do is all the negative phases will represent in the positive side. You can see that this portion, this is the portion. I make it here, we'll get it as a AC, and this portion I will make it in the positive side, we'll get it as a BA, and this portion I will make it in the positive side, we'll get it as a CB. So like this, I want to draw as a line to line voltage. Now I have all the line to line voltage. Only thing is I started here 30 degrees delay. If you start same thing, if you represent three phase supply and you mark the AB, BC, CA and invert it, we'll get other three phases. So I mean line to line. Now how to draw the output voltage? Now this is the common, everybody can draw three phase supply and providing as a pulses, then draw the line to line voltage. Once if you draw the line to line voltage, I have to mention what is your output. How will you draw the output voltage? Now we can see here, first thing, any instant. Now we will start this crossover. How to draw output? Identify what are the devices are forward bias and firing pulse is available or not. If pulse is available, what is our output? That's it. So now at this, I want to start it at omega t is equal to 30 degrees or alpha is equal to 0, because we already provided firing pulses alpha is equal to 0. Now alpha is 0. Who will fire first? Which is more positive, which is more negative? From this point onwards, A phase and C phase are exactly same. From there onwards, A phase is more positive. That means A phase is more positive, is belongs to what? T1. And which is more negative? More negative is B phase. B phase is belongs to D6. So then your conduction devices are known to you, T1 and D6. If T1 and D6 is known, and you can shade the output is what? Positive group devices is A, and then negative group devices is a B. Your output is AB. Just shade the AB from this point onwards. So now AB is available. I am shading the AB. How long? Every instant you check it. Every 30 degree you check it. Otherwise, what will happen? I'm coming starting this point. Your output is started here, green, whatever I'm drawing, that is starting point is this, and now I shade the AB and check it once again whether it is continue AB only. At this point what will happen? A is still more positive and B is still more negative, therefore AB will continue. Again you'll shade another 30 degrees, you check it one more time and you can see here what happening. A is still more positive, but B phase is not negative. What will happen? Not more negative. That's the reason. You can see that B phase magnitude is reducing, negative magnitude, but C phase magnitude is increasing. That's why lower group is going to be changeover. Instead of conducting D6, now the device conduction is a D2 device. Then what is our output voltage from this point onwards? Anybody? Just interact. If you have any doubt, you ask me. So now what will happen from this point onwards? B phase device is less negative, but C phase device is more negative. But still positive devices remain same because it is still more positive only. Then what you can represent? Our output devices are T1. Lower group is what? It is transferred to D6 to D2. Reason is D6 device means B phase is less negative and C phase is a more negative. So that's why D1 and then D6 is D1 and D2 is going to be forward bias. So that is the reason our output voltage is what? VA. D2 is connected to which phase? As you know that 135462, no, 135 462. Then D2 device is connected to C phase. What is our output voltage? AC is our output voltage. Now you shade AC from here onwards. It goes to AC. Now AC. Again you check it after 30. Every 30 degree you can see. And what will happen? Now you can see D2 will remain same because it is more negative. A phase is still more positive. Then again AC only our output. You shade AC. Then you can see that it is changeover. What will happen? Now upper side is going to change over. So what is upper side? A phase magnitude is less positive than B phase. And that is the reason A phase device is going to be turn off and then B phase device is going to be 5. What is B phase device? T3. So now we want to change over to B phase. You check pulse is there for B phase device or not. What is B phase device? T3. T3 pulse is available at this instant, starting. If pulse is not available, A phase device will continue to conduct. Now what will happen? The upper group device is changeover. So what is changeover? Instead of A phase, B phase device is going to conduct, but still D2 will be remains. That's why C phase device will be remains in the lower side, but upper side is going to change over. So that's why we transfer to BC. Again you can see it is continue and it will come, and this is your output voltage waveform for alpha is equal to 0 degrees. Is it clear? So I am drawing output voltage waveform for alpha is equal to 0 degrees. What you need to notice, we have to see that whether it is a more positive or more negative. So in that logic we can able to draw the output voltage waveform starting. We can start here and you can shade this, and it is going to be, then it is transferred to BC, then it is transferred to PA, then transferred to CA, then CV, and cycle is going to be repeated. Now how many pulses we are providing in the output? There is a 1, 2, 3, 4, 5, 6. So totally you are getting 6 pulses in output. But we are operating alpha is equal to 0. That is a maximum output. Whether you use the 6 pulse converter or a 3 pulse converter, output voltage, maximum output voltage is same for both cases. Whether it is a 3 pulse converter or a 6 pulse converter, that's why you are getting as a 6 pulse output. That means that it is not a 6 pulse converter, it is only the 3 pulse converter. But except alpha is equal to 0, all other angles you are getting only 3 pulses in the output. So this is the for alpha is equal to 0 instant. Now I want to change alpha 0 to some 30 degrees. What modification is required from this point onwards? What I have to do? Alpha is equal to 30 degrees. For now you have to provide the firing pulses for alpha is equal to 30 degrees. Whatever I provided the pulse here, this is for 0 degrees. Now I have to provide alpha is equal to 30 degrees pulse. What change? Instead of starting here, you can start pulse will be here. That's all. So now this is your firing pulse for T1 and this is for firing pulse for T3. What I did is I starting point will change. That's it. This is the firing pulse for T5. That's all. What I have to do, I have to start here 0, count 30 degrees and then put the pulse. Here is 0, count 30 degrees, put the firing pulse. And for T5 here. So that's why I drawn the line. In exam also you try to draw the parallel lines and each line is 30 degree, you mark it and you can easily identify. So the one important question, whether it is a fully controlled rectifier or a semi-converter, they may ask in the exam also. So what they may ask is the different values of alpha. But you must understand how to draw the output voltage waveform. You can draw supply, then you put the firing pulses, then draw the output voltage waveform, and now you can put it this alpha is equal to 30 degrees. Starting point is here now. VAB only output, but starting is here rather than here. So now what you have to shade? VAB shade. I shade the output voltage AB. But this point, what is noticed that lower is changeover. Then what will happen your output? VAC. So instead of AB, it is transferred to VAC. How long? You can see up to this VAC is only more positive, more negative only. A phase is more positive. Here is A phase is more positive and C phase is more negative up to this point, and I mentioned VAC. But after this line, you can see upper side. What is happening? What is happening? A phase is less positive, B phase is more positive. Now tell me anyone whether I have to shade BC or I have to shade AC only output after this point. So after this point, what I need to do? Whether I have to transfer to BC, I have to transfer continue to conduct AC only. What output you are expecting in the output side from this point onwards? A phase is less positive, B phase is more positive. If I want to transfer to B, what other condition need to satisfy? Firing pulse is available or not? Now you come down this point, pulse is available, not available, only red line. This is the starting pulse. In this area, no firing pulse. That's why even though B phase is more positive, but A phase device only continue to conduct. Reason is B phase device not having firing pulse. So that is the reason it will continue to conduct AC line only. How long? Until firing pulse is available. Now at this point pulse is available. Now what will happen? Now it will transfer to AC. Now your output voltage is AC. And again after this instant, what we need to see? Lower group. So lower group changeover. What is changeover? Instead of C phase, now it goes to as A phase is more negative. That's why your output voltage will be, what will happen? BA. Your output voltage is BA. And then we can see again, still same, it will continue to conduct. And then it will coming down because next C phase device is not having firing pulse, even though at this point it is C phase device is more positive than the B phase device, it will not transfer because at alpha 30 degrees pulse is, this is 0 line and this is the 30 line. That's why it will continue to conduct in the previous BA only, then it will shift it to CA like this. Then it is goes to CB like this. So now you can see what is our output. This is starting point. This is the starting, and we are getting from here to here is one common pulse, and this to this is another common pulse, second pulse, third pulse, this to this is one set. Repeated pulse. So what is repeated? This portion is the repeated, and there is another, and this one is a third one. So therefore totally 3 pulses will be obtained. So that is what you can able to get it as a alpha is equal to 30 degrees waveform. And suppose alpha is equal to 60 degrees. What I have to do? What change we require? So now alpha is equal to 30 degrees Just a minute. Yeah. So alpha is 60 degrees. How to provide the firing pulse? How will you provide? Again, same one more step you change. This is starting pulse for alpha is equal to 60 degrees, and this is starting for T3, and this is starting pulse for T5. That's all. Now you can start here. Your output voltage will get like this. Alpha is 60 degree. Next it will transfer. Then output will be like this. I will show that anyhow separately. So because it's coming. So now if you increase the alpha value, only you are shifting the one line for firing pulse. Like that you can see this is the alpha 30 degrees firing pulse, and you can shade whatever I shaded previously, you can shade that, and alpha is equal to 30 degrees output is like this. I already drawn. This is the repeated pulses here. 3 repeated pulse. That's why it is a 3 pulse converter starting here, and this will be ending here. This is 1 pulse. This is another pulse. Third pulse. That's why these are the 3 firing pulses will be available. So now we can able to get this is a 3 pulse converter. Alpha is equal to 30 degrees. Similarly, if it is what are the instant it will conduct, I already explained omega t instant, or alpha is equal to 30 degrees is nothing but omega t is equal to 60 degrees. This one. So now omega t is equal to 60 to 90 degrees. T1 whatever the devices are conducting I mentioned here, and then RMS output voltage totally each device we can or phase, whether it is a T1 or it is a D4, it will conduct 120 plus 120. So that's why 240 by 360 root 2 by 3 I naught. So A phase is like this. Similarly B phase, C phase also same thing. Now you can go for alpha is equal to 60 degrees. How will you draw this alpha is 60 degrees? Starting this is 0, because pulse is started at this point 0, then 30, 60. So put alpha is 60 degrees. This is the firing pulse for T1, and this is 0, 30, 60. This is firing pulse for T3. Same thing T3 and then T5. So lower side anyhow diodes will not change anything, because most negative starting point, from that onwards the during negative instant that corresponding device will conduct. Now what is noticed in this, if you make it alpha is equal to 60 degrees, you are getting exactly natural 0 point. So if you increase beyond that, you will get it as a discontinuous. Suppose alpha is 90. What is our output voltage? You can get it alpha is 90 degree. Instead of starting here, you can start here at this point. So it will a natural 0, and then it will be starting will be here, and we'll get natural 0. Starting will be here, we'll get natural 0. So like this you can able to get it your output. So in that the way you can see I drawn separately. Alpha is equal to 0 degrees as usual of all 6 pulses will get it, and this is alpha is 30 degrees, alpha is 60 degrees, alpha 90 means starting will be here and ending is same, but we'll get the gap here, that will get it as a 90. And this is A supply, 3-phase supply. You can write Vm sin omega t, Vm sin omega t minus 120, then plus 120, and VAB, how will you get it? VAN minus VBN, and AN is Vm sin omega t, and Bn is omega t minus 120. Sin A minus B form you expand and simplify, will get it as a this one. This is a AB value. And similarly, why we require that? While you are deriving that, you can substitute AB, BC, CA. These are the line to line voltages. V line to line voltages. This. Then you have to take it as a average expression. Now we will get average expression for two things. Average expression. One is alpha is equal to continuous mode and discontinuous mode. Up to 60 degrees is a continuous, and discontinuous greater than 60 degrees. Now as usual, integral, it is a 3 pulse converter, 3 by 2 pi, and then alpha to 30 degrees starting point, ending point are 2 instant. So because magnitudes are different, first instant is AB, another instant is a AC. So that's why up to 90 degrees with respect to omega t I mentioned. So you want, you can see that also here. You can see here This is starting point alpha plus 30. Ending point is, you can see, 90 degrees. That's why I mentioned VAB is a alpha plus 30 to 90 degrees. 90 to remaining voltage total 120 degrees. So you can see that total is 120 degrees. That will be as a AC voltage, like that, any value. Now you can see that AB and then AC. You know what is the AB? Root 3 Vm sin omega t plus 30, and AC root 3 Vm sin omega t minus 30, and then integrate sin omega t is minus cos omega t. Like that, you simplify, you will get it as a, what is your average output voltage. Once if you get the average output voltage for this is a VDC for continuous mode of operation. And discontinuous mode of operation, starting alpha plus 30, ending is common. So that will be as a alpha plus 30 plus 120. You can give it, you will get it as a ending point. Suppose this is a natural. That means it is not 120, total 120 will not conduct here. Starting is differ, ending will be natural pi. So that you can use it for discontinuous mode of operation. All I given derivation part also. This is the, in this case, one beauty you can notice whether a continuous mode or a discontinuous mode average expression we are getting as the same 3 root 3 Vm by 2 pi into 1 plus cos alpha. So this is the average expression for continuous mode and discontinuous mode of operation. Even if it is RL load also, you won't get any negative. In this gap revealing diode is going to be 5. So that's why your expressions, everything is going to be the same. So now this, for your reference purpose, I give an empty sheet here. You can draw the firing pulses at any particular instant. Alpha is 0, want to draw, or alpha is 30 or 60. You can practice with providing as a firing pulses. Like this, you can provide the firing pulses for T1, T2, T3, and this is a line to line voltage also I mentioned. You can shade your output voltages according to alpha, and you just practice. Otherwise, I will show the graph sheets also. This is for practice, a given empty sheet. And this, in exam, if you are unable to draw complete phase voltage, firing pulses, line to line voltage, you can directly draw the output voltage waveform for the particular value of alphas. You can see alpha is 0. 6 pulses will get. Alpha is 15 degree or 30 degree. So based on that, so you will get it as a, this is the 3 pulse, and here is a 3 pulse continuous mode of operation, and set alpha is 60 degrees, then the 90 degree you will get as a discontinuous mode of operation. Like this also you can draw, but they will reduce some marks if you are not specify the firing pulses and then phase voltages, line voltages and all. And this is the graph sheet. If you want, you can practice 3-phase supply, firing pulses you can give, and then line to line. What I mentioned, no, supply is started here, and 130 degree you can shift in this. You can redraw the same 3-phase supply and shift the negatives to the positives, like that. And this is for alpha is equal to 15 degrees waveform. This is the pulse provision, and for alpha is equal to 30 degree. I drawn all the different values of alpha. Just you want, you can practice by seeing this. But in exam, we don't require the graph sheet, all these things. You have to draw as a lines and you can provide that. And this is different values of alpha 90 degrees, and then this is 120 degrees. And this is the just textbook also mentioned like this. But if you draw directly like this, they may reduce the marks. And this is the for RLE load. Only E load case, I told, no, instead of getting the 0 instant, you will get it as a some magnitude of voltage, whatever voltage you are going to provide. So this is your derivation part. 3 by 2 pi alpha plus 30 to 90 VAB, and then 90 to 120 AC, and you just integrate this portion whether it is a continuous or a discontinuous, we'll get the same expression. So this is the today's class. If you have any doubt, you can ask me. I will share anyhow this PPT. Anything? If you have any doubt, you can ask me. Otherwise, you can leave.